Good evening, and this is another webinar in the series of webinar being organized by local chapter of INAE. Today's speaker, as you might have seen in the notice, is Dr. Kinshuk Dasgupta. I think headquarters is displaying my profile. So maybe we can have profile of Dr. Kinshuk Dasgupta here. He joined Bhabha Atomic Research Center as a scientific officer after completing his Bachelor in Engineering from Jadavpur University, Kolkata in 1999 and completed his PhD in Chemical Engineering from Institute of Chemical Technology, Mumbai. And during 2018-19, he was at University of Cincinnati as a Fulbright visiting scholar. He has received various awards, and the most prestigious and the recent being Shanti Swarup Bhatnagar Prize in 2020 in Engineering Science. And that award, Bhatnagar Award, has been conferred upon him for his work on carbon-based nanomaterials and composites, leading to the development of Bhabha Kavach, a lightweight import substitute ballistic resistance jacket for Armed Forces of India. Dr. Dasgupta has filed 2 patents, authored 3 book chapters, and has close to 100 publications in various journals. Currently, he is serving as head of advanced carbon materials section in the materials group in BARC, and also has a joint appointment as associate professor in Homi Bhabha National Institute. Now, I think go to next, please, abstract of the talk. Today he will speak on engineering of carbon nanotubes and their applications. Carbon nanotube is an exotic material having many attractive properties. However, to utilize this material for practical applications, large-scale economical synthesis of CNT is required. Out of different techniques, fluidized bed and floating catalysis, chemical vapor deposition techniques are scalable. To scale up any process, one needs to understand the reaction mechanism, the rate controlling steps, and the overall rate of reaction. And in today's talk, these aspects of CNT synthesis will be discussed by Dr. Dasgupta. After making CNTs in large scale, they have been used in various applications. How CNTs improve the performances of materials will be covered in the talk with special reference to Bhabha Kavach, an indigenous lightweight ballistic resistance jacket. The technology of Bhabha Kavach has been transferred to the industries for large-scale deployment of the product to Indian Armed Forces. And I was speaking to Kinshuk Dasgupta just before the talk, and he told me 4 companies have taken this technology so far. One is Bidhani, which has already received orders. Let us hear more from Dr. Dasgupta.
Thank you, Dr. Grover, for the nice introduction, and good evening to all the attendees. And it is indeed a great honor for me to get the opportunity to speak in this forum. I must thank Dr. Mrs. S.B. Roy, who took a lot of efforts for conducting this talk, and other INAE dignitaries for attending the lecture. So before I start, let me share my slides. I hope my presentation is can be okay. All right. So the topic, as you can see, is engineering of carbon nanotubes and their applications. And before I go to my actual talk, I would like to thank the contributions of my team members, my mentors, as well as collaborators from BRC and other institutes. Now, what is carbon nanotube? So if we take hexagonally arranged carbon atoms, sp2 hybridized, which we call a graphene sheet, and try to roll them seamlessly, so we end up with some tubular structure, which is called carbon nanotube. So if it is a single sheet and we are getting a single tube, so it is called single wall carbon nanotube. And depending on how we roll it, it can be either metallic or it can be semiconducting. And if such concentric tubes are there, we call them multi-walled carbon nanotube. Now, why carbon nanotube is so much attractive? So if I compare the properties of carbon nanotube with other forms of carbon as well as the steel, which we use day-to-day basis. So if you see the strength, the carbon nanotubes, both single wall and multi-wall, they have almost 10 times higher the strength. Young modulus also 1 order higher. And see the density wise, density of steel is 7.8 gram per cc, whereas carbon nanotube is in the range of 1.1 to 1.3. So the specific strength is very high, means if you consider the strength to weight ratio. And also these nanotubes, they have excellent thermal as well as electrical properties. And due to these properties, they are finding applications in various fields, like in composites. So in composite, we use them as filler material, which can be a metal matrix composite, a ceramic matrix composite, or a polymer matrix composite. And also we find applications in water treatment, gas adsorption, energy storage. And in these applications, mainly the high specific surface area of carbon nanotube is utilized. Then also carbon nanotube is used for sensor applications, for catalysis, for drug delivery, also fluidization. And at Bhabha Atomic Research Center, we are focusing on certain applications of carbon nanotubes. If you see the left hand side topmost, there carbon nanotube is used as a filler in ceramic matrix, like in boron carbide, which is a ceramic. We add carbon nanotube to improve their properties. Then also in polymer, like ultra high molecular weight polyethylene, there also we have used carbon nanotubes to improve their properties. And both of them have been used for making Bhabha Kavach, which is a lightweight ballistic resistant jacket. I'll come into that in the later part of my presentation. And we can even dope heteroatoms like boron or nitrogen into carbon nanotube, and we can alter their properties, and that we have done there here to understand how this doping helps in improving the hydrogen storage, and also we studied the kinetics. There is one special class of material which is called carbon nanotube aerogel. It is a 3D structure, self-assembled 3D structure of long carbon nanotubes, and this material also we are synthesizing, from where you can get carbon nanotube fiber. They can be used for making flexible capacitors, for piezo-sensors, chemical sensors. Carbon nanotubes are also used for metal ion separation, like we have prepared carbon nanotube polymer composite bead for rare earth extraction, then water purification, and also actinide separation. But for all these applications, we require the carbon nanotube to be produced at a large scale. So first today I will talk what are the methods by which we can produce the large scale carbon nanotube. So what we are employing at ARC is called fluidized bed chemical vapor deposition. So why fluidized bed? Because this fluidized bed, it gives the maximum utilization of surface area for a gas solid reaction. We'll see in the next slide that the synthesis of carbon nanotube basically it is a gas and solid reaction. And also high throughput is there in fluidized bed. We have the facility where we can make almost 1 kg of carbon nanotubes per day, which is a huge capacity. I think that is the highest in our country at present. And if how carbon nanotubes look, means it is nano. That means the diameter is in the nano dimension, but the length can be in the micron or in the millimeter. So if we see under electron microscope, this second image is the electron microscopic image, TEM, transmission electron microscope, where you can see a tubular kind of structure where the core is hollow. And if we go for further high resolution, that is high resolution electron microscopy, you can see the number of walls of carbon nanotube. And by this method, we are able to produce almost 98.5% pure carbon nanotubes. So what are the basic requirements for making carbon nanotube by chemical vapor deposition? So we require a carbon source like hydrocarbons. We require a catalyst, generally transition metal catalyst or their alloys are used like iron, cobalt, nickel. And we require a catalyst support material because this catalyst needs to be dispersed, otherwise they will agglomerate, and once they agglomerate they cannot catalyze carbon nanotube. So generally alumina, magnesia, silica, zeolite, or we have used carbon black that are used. We require a carrier gas like hydrogen, nitrogen or argon to dilute the hydrocarbon. Otherwise what will happen, the hydrocarbon, if their partial pressure is high, they will simply crack and give you the soot kind of thing, which we don't want. Also temperature is required to give the required activation energy for the growth of the carbon nanotube. So what we are using as carbon source, hydrocarbon, we use acetylene, which is commonly available and cheap. As support material, we use carbon black. There is a beauty of carbon black, which I will discuss in the next slide. So people generally they use like alumina, magnesia. These are costly materials and you require further processing steps to remove those materials from carbon nanotube. But in carbon black, it is first of all, carbon black is very cheap, and also you can remove them very easily, that I will discuss. So that is why we have used the carbon black. So by using these materials, you can really make the product a cheap product. If you use a raw material which are cheap, then you can end up with a product which are cheap. And carrier gas, we have used argon, catalyst, ferrocene. Ferrocene is a organometallic material which on heating will release iron nanoparticles. So generally synthesized in the temperature range of 700 to 1000 under atmospheric pressure. And just I wanted to tell about the carbon black. The beauty of carbon black is that their primary particle size are nano range. This is around 30 nanometer. But it is very difficult to fluidize the nanoparticle. But this carbon black, they self-agglomerate and form soft agglomerate in the size range of say 10 to 500 micron, which are easily fluidizable. And we can sieve them, get the proper size range, and fluidize them and grow the carbon nanotube on that. So what is fluidization? If I show this video, see, like this is a circular motion. We consider these yellow particles as say as carbon black. So these carbon blacks are fluidized by passing the argon gas from bottom. If I see this schematic, so argon along with hydrogen, we pass through this, and here the carbon black is fluidized, and once the temperature is reached, here we keep the ferrocene, which is a preheater region. So from here the ferrocene vaporize and they come here, and on cracking they will deposit iron nanoparticle here, and then carbon and hydrocarbon comes, they also get cracked and carbon nanotube grow. How they grow I am showing in the subsequent slides. So as I told, the fluidization is very much required. So we need to ensure whether proper fluidization is happening or not. So there are famous Argon equation, and if we perform this kind of study, like if we measure the bed pressure drop against the superficial gas velocity, we end up with initially with the increasing pressure drop, and at the beginning of the fluidization, the pressure drop just drops and then it remains constant. So by this experiment, we can find out the minimum fluidization velocity, and we need to operate above the minimum fluidization velocity so that all the particles are in a suspension condition and we can utilize the maximum surface area. Now, to understand what is happening inside the reactor, we need to carry out several experiments. So we varied different process parameters, and I am explaining why we varied. The first is the temperature. Like if we vary the temperature, we will come to know what is the activation energy of the process. So if I get an idea of the activation energy, then I can understand or estimate what can be the rate controlling step. Like there may be three possibilities in gas solid reaction. One is the external diffusion, which is that means the bulk diffusion. Then there can be a diffusion through the pores, and which is called internal diffusion, or there can be a chemical reaction. Now, if my activation energy is high, that means chemical reaction is the dominant, that is the rate controlling. But if my activation energy is low, like typically below 10 or 15 kilojoule per mole, so then we can consider diffusion control regime. So what we are doing, temperature, from temperature we can understand that what is the activation energy. Then by flow rate changing, we can understand whether it is a diffusion control. So this is the external diffusion control. By changing the carbon black agglomerate size, we can understand the internal diffusion control, because when we change the size, the pore size and pore diffusivity changes, so the effect will come. Then also we change the initial bed height, that also give you the internal diffusion. And this catalyst concentration and partial pressure of hydrocarbon and hydrogen, they show us that whether there is a chemical reaction control or not. And finally, time of synthesis, this shows whether there is any deactivation of the catalyst or not, because it is a catalytic activity and there is always a tendency that the catalyst gets deactivated. So we can understand the kinetics of deactivation by studying the last parameter. Now I am showing the effect of temperature. So what we saw, that at low temperature, that is in the range of 700 to around 800, means up to 800 degrees centigrade. So there the activation energy is around 47 kilojoule per mole, and there is a change in mechanism above 800. So 807 degree typically. So this part is, you can see the low activation energy, that means it is a diffusion control regime, and this is a chemical reaction control regime. Now, as I discussed, so we change the superficial gas velocity in the two regime, both at 800 degree, which is the if we go back to the previous slide. So I am considering this is the two regime, right hand side this one and left hand side this one. So I am carrying out experiments in both the regime, and if I see the carbon deposition, CNT deposition rate, it is not getting affected in both the temperature range. So that means we can conclude that external diffusion is not the rate controlling. That is why there is no effect on the carbon nanotube deposition rate at these temperatures. Then we change the carbon black agglomerate size. So what we could see, that at low temperature there was not much change in the deposition rate, but at high temperature, that is at 1000 degrees centigrade, there was significant change. So then we can tell that at low temperature region, that again internal diffusion is not affecting, but at high temperature it is affecting, and that is why we got a low activation energy in the high temperature regime. So if we draw 1 by d, d means diameter of the agglomerate, with the rate of carbon nanotube formation, we could get a straight line from where we can derive an equation by which we can describe the process, the reaction rate at high temperature regime. Now, what is happening at low temperature regime, and overall what is the reaction mechanism? So we arrived at that by performing all these experiments. Now I am explaining what we could understand. So this is a schematic of a fluidized bed, and these black particles, they are carbon black agglomerate, soft agglomerate. So if we see this, these are the primary particle, the small balls, and the small balls, they agglomerate, and this is one small agglomerate. Means this full sphere is one agglomerate, that is carbon black agglomerate. So what is happening? There are two phases in the fluidized bed. One phase is called emulsion phase, where this carbon black agglomerate and the gas, they are homogeneously mixed, and another phase called bubble phase. That means excess gas. So in the bubble phase, what happens? This argon, hydrocarbon, all these things are there excess. So in the first step, the acetylene, which is my source of carbon, that transfers from the mass transfer is from this bubble phase to the emulsion phase. Then in the next stage, from the emulsion phase, there is a mass transfer on the external surface of the support, that is carbon black. And then in the third step, from external surface, the carbon, that acetylene, has to diffuse and reach to the catalyst particles which are sitting inside the pores. So once they reach there, then what happens? They get absorbed on the catalyst surface. These are the iron nanoparticles, and the hydrocarbon first get absorbed onto that, and after absorption there is a catalytic reaction, that means pyrolysis it is called. So hydrocarbon, they crack into carbon molecules and the hydrogen that comes out. So reaction on the catalyst surface to produce carbon molecules, and these carbon molecules, they have solubility in the carbon catalyst, this iron catalyst. So they have a solubility, limited solubility. So they go on getting soluble, and then once they reach saturation and then supersaturation, after supersaturation, the carbon would like to come out in a tubular form. So because at that particular condition, the tubular structure is the thermodynamically stable structure, so it will try to come out as a tubular form, and that is called the nucleation, and further the growth of the carbon nanotube. And whatever gaseous products, that is hydrogen and other gaseous products, they will be dissolved and follow the reverse path. That means initially they will come out through the pores, then from the pores to the external, then in the bulk, and finally it will come out. So these are the 11 steps which we proposed during the synthesis of carbon nanotube in fluidized bed. And if I just write them in this slide, I can say that the first 3 steps, they are related to the mass transfer. Then next 4th to 9th, we can say, in fact up to 8th, we can say this is related to chemical reaction, and again 9th to 11th, this is related to another mass transfer. So we can write now the mathematical equations related to the steps which are of concern. Means at the low temperature, as I have told, that chemical kinetics is the rate controlling. So we can, for each step, we can write some equation, because we need to understand, unless we develop a mathematical model, we will not be able to scale up the process. So this mathematical model is required to understand the rate of reaction and also to get an expression for the rate controlling step as well as overall rate of reaction. So as I told, acetylene is coming and reacting with S. S means a site. This S means a catalyst site, and they are getting adsorbed. Then after the adsorption, there is a dissociation in the carbon molecule and then hydrogen comes out. Then once again this adsorbed carbon, they react with excess acetylene, they get saturated, hydrogen comes out. Then the saturated one once again reacts with acetylene, becomes supersaturated, then hydrogen comes out. And finally from supersaturated, carbon nanotubes comes out and this comes back to the saturated level. So except for the last step, all are reversible reaction, but the last step is definitely irreversible. So we can, this is the final form of equation if we consider each step individually as rate controlling step. And what is our aim is to see, if we look at these equations, you can see CT means catalyst concentration. So for all the equations, the catalyst concentration vary linearly. So let us check. So we varied at two different partial pressures of hydrocarbon. We changed the catalyst concentration and we could see if there is a linear variation with respect to the rate of carbon nanotube deposition. Obviously, they reach to some saturation value where it is constant. And if we see the partial pressure, so the partial pressure, they vary differently for different steps. So what we did, we tried to plot this data, we tried to fit with different equations, and we could see that the fifth step, that means this equation could be properly fit into with the data. So then we can say, okay, this is the rate controlling step. That means our dissociation of adsorbed acetylene into carbon molecule, that step is the rate controlling step for the carbon nanotube production in fluidized bed synthesis of carbon nanotube. So we could find out the different rate constants, and this we published in the ICH journal. And what we did, that our model, we tried to fit the data of all the published, means other authors, they also published their data. So we took their data and tried to fit in our model, and we could show that yes, this model is universal, and really we could fit others' data also into this model. We also studied the deactivation of the catalyst. So what happens in case of deactivation? If you see that if this is a TEM image where I could show that during deactivation, the catalyst particle, they get covered with unwanted carbon forms, and then they cannot further catalyze carbon nanotube. Like you can see only one carbon nanotube here just started growing and then it got deactivated. Now what causes deactivation? Like what happens, this carbon, the supply of carbon molecules, they should match with the supply, that growth rate of the carbon nanotube. If there is more supply, or if the surface of the catalyst, the active part, it reduces, then there is a relatively more supply of the carbon molecules than the required. So what will happen? There will be a soot formation or a amorphous carbon coating on the catalyst particle, which cannot further catalyze the growth of the carbon nanotube. So this deactivation also we could model with an equation, and we could predict that up to what time you should synthesize the carbon nanotube. Now after we get the nanotube, we need to characterize. Means can I say the product is carbon nanotube, or it is an amorphous carbon, or other forms of carbon? So first is, okay, we can see under microscope, but taking to microscope takes some time because you require the sample preparation. What we can do, the first step, Let us see under Raman Spectra. So Raman spectroscopy is a method by which you can characterize your product very quickly, and it can give you a bulk, means you can take samples from a large number of positions and you can see their Raman spectra, which is very quick technique. And typically a carbon nanotube, they have three characteristics peak. One is called D, another G, another 2D. So if it is multi-walled carbon nanotube, you will get a D peak slightly high, but in case of single wall carbon nanotube, there should not be any of the D peak. I'll show in the subsequent slide. The D peak is not there, rather there will be another peak which is called RBN peak. So by seeing the peaks, we can tell, okay, this is a single wall carbon nanotube, or it is an amorphous. In case of amorphous carbon, the D peak will be higher than the G peak. So if the D is higher than G, we can tell, okay, this is not at all carbon nanotube. So if it is D is low with respect to G and there is a 2D peak, then we can say, okay, this is carbon nanotube. But depending on the D intensity, we can tell whether this is single wall or multi-wall. So also we do thermogravimetric analysis in the oxygen atmosphere or air atmosphere, and by which we can find out the relative proportion of different phases. Like we can tell what is the amount of catalyst in the product, what is the amorphous carbon concentration, and what is the carbon nanotube concentration, because the oxidation starts at different temperature. Like if it is amorphous carbon, then amorphous carbon being a high energy phase, it starts oxidizing earlier. So we will get, and secondly, if we take the derivative of them, we get a different rate of reaction. So from there we can come to know how many phases are present. So then we take it to the transmission electron microscopy, which should show like this, that it is a tubular kind of structure. And if we go for high resolution electron microscopy, then even we can count the number of walls. And this is like, this is the inner diameter, this is the outer diameter, and around 8 to 13 numbers of walls are present in the nanotube that I can show here. Now, if I want to produce single wall carbon nanotube, that means there is only one wall is present, then fluidized method generally does not give you the single wall carbon nanotube. We need to go for a floating catalyst chemical vapor deposition, and a carbon source methane is used, because methane is having one carbon, so it is easy to control the input of carbon by using methane. Then other things are same, ferrocene we take, argon we take. One more important thing is sulfur. So sulfur is used as a growth promoter. What happens, sulfur, they partially coat the catalyst particle and allow a very small portion to be used for the nucleation, and that is why the diameter is small and we end up with only single wall carbon nanotube. Now how it should look under TM, here it is looking, say you can see the single one tube, but you are hardly seeing any thickness of the wall, and generally they come into bunches. Why in bundles? Due to their very high surface energy, they try to minimize the energy and come in bundles, and it is very difficult to separate them. But if you are able to separate by means of sonication and high energy sonication, then you can see this single nanotubes, that is single wall nanotubes. And if we see under Raman spectra, as I told, the D peak is gone. Rather you get a RBN, which is radial breathing mode peak, and from this peak you can even calculate the diameter of the carbon nanotube. If you do the TG thermogravimetry, here also there is a sharp fall you can get, because the walls is only one wall. So as soon as it starts oxidizing, there is a sharp fall in the mass in the oxygen atmosphere. Now we studied the effect of partial pressure on the synthesis rate of the single wall carbon nanotube. Here it is slightly different. In case of multi-wall, you got the curve like it is increasing with a decreasing slope. But here, after some partial pressure, there will be a decrease of the rate of synthesis due to it follows a different rate law, and that is why generally this single wall carbon nanotubes, they are produced at a low partial pressure of hydrocarbon, and that is why we even cannot produce the single wall nanotube at as much higher rate as multi-wall carbon nanotube. So always the synthesis rate of single wall carbon nanotube will be low than the multi-wall carbon nanotube. So we could do some publications on that. Now I am coming to the applications part. So after synthesizing the nanotubes, where we apply, the first thing is I am showing on the separation sides. Means like this example is for the rare earths. So as you know, rare earth materials are very important materials, and really they are controlling present world. All our this computer hard disk, even in mobile phone or in windmill, we use rare earth magnets. And the separation of rare earth is, we have developed a process which is called using polymeric beads. And what happens, the carbon nanotube, they alter the pore structure of these beads. Like if I take a cross section of the bead, so here it is a hollow core, and the thickness, this is a porous thickness. So inside the hollow core, the extractants are there, generally DEFA or PC88, this kind of extractants are used for rare earth extraction. And carbon nanotubes, they are sitting all over the polymer, and what they do, they control the pore structure in such a way that the movement of the ions, they get facilitated. Like if I draw the weight distribution ratio, like we took the yttrium, where we did not, with the polymeric bead, where we did not add the carbon nanotube, the ratio was around 20, very precisely around 18, and which improved more than 6 times when only 0.25% carbon nanotube was used. So we get some scheme for that, means how it helps. Like even the ligands, which are very much specific to the rare earths, they get functionalized with the carbon nanotube, and then this can attract the particular you can say ion, which is here the rare earth ion. Like here I am showing a transmission electron microscope where we took the NdFeB, that is neodymium iron boron magnet, that scrap, and we made it into solution, and from there specifically Nd we could get attracted on the carbon nanotube, which is functionalized with the ligands which is specific to Nd. Similarly, functionalized carbon nanotube has been utilized for the actinide separation. Like here, different ligand has been used, like AA, amidoamine. In this bottle, if you see, it contains uranium and americium, and then a multi-wall carbon nanotube functionalized with this amidoamine. They were added and shaken, and once you stop all the ions of uranium and americium, they got absorbed onto this, and you get that ion-free water. So like this, it has been used to understand how they behave for the americium, plutonium, and all these ions kinetics of adsorption vary with the functionalized carbon nanotube. There's another interesting application, like I'm talking about a tube. So inside is hollow, definitely. So what happens if we can fill some metal into the hollow space? Like if we put some magnetic material, first of all say iron, so they behave in a different way than the bulk material. So people have reported that single metal in that insertion inside the cavity, but here what we did, we tried to put bimetallic, like samarium cobalt is a very strong magnet, SmCO5. So we wanted to see whether such phase, we can form that phase inside the nanotube and whether that can be used as a nanomagnet. And we could successfully make the carbon SmCO5 phase inside the carbon nanotube. And the application is there in the hyperthermia kind of application. And recently, we have used the carbon nanotube for the capture of say virus. Like carbon nanotube, as you can see, I have shown in the first slide, there is a methodology called carbon nanotube aerogel, which is 3D structure. From there, you can make some kind of filter where the carbon nanotubes are randomly oriented, but the pore size are such that you can trap the virus. Here we have taken P1 phage, which is a virus to the bacteria, but having a dimension which is similar to that of the COVID. So we could show almost 98% of this phage material could be trapped by using single layer of carbon nanotube filter, and also the flow was, means, see, if we can make a filter or say mask using this material, it should not only capture the virus, but also it should allow the respiration to happen. So the pressure drop against this was not high. It was at par with the present N95 mask, but the capture of virus or say this particle was very, very efficient, more than 98%. And not only you can capture, you can characterize whether this, what is this, because this can be any other dust particle as well. So by using Raman spectroscopy, you can identify what you have captured. Now I will come how carbon nanotube improves the property of ceramics as a filler, because this is having very good application in the impact kind of application. So here boron carbide is a ceramic. As we know, we are using boron carbide and atomic energy as control rod material, and boron carbide is also used in other like armor applications, and even for the cooling purpose it uses. So here I am showing that if we add carbon nanotube during that hot pressing of boron carbide, boron carbide is generally produced by hot pressing. So when we add carbon nanotube, what happens first of all to the structure? So this is without carbon nanotube, and we could see some kind of porosity is present. And when we go on adding with 2 volume percent, then 5 volume percent, then 10 volume percent, we could get the density, full density, but at higher volume percent you get the agglomeration. And if we check the properties, what happens? We have added not only carbon nanotube, also the other carbon based materials like carbon fiber and graphene nanoparticle. Why? I am telling you, carbon nanotube is considered as a one-dimensional material, graphene nanoparticle is a two-dimensional material, and carbon fiber is a macro material which is in the macro dimension, not the nano. So how their addition affects the property of boron carbide? Here you can see that the hardness, which is very important for the boron carbide, generally initially it improves, and improves due to the improvement of the basically the porosity, nothing else. But then with carbon nanotube, the hardness almost remains same. It does not come down unless at high percentage where agglomeration takes place. But for say graphene nanoparticle and other carbon fiber, it deteriorates because of the fact that these are the soft phases. these are the soft phases, graphene as well as carbon fiber, and they decrease the hardness. Fracture toughness, which is very important because ceramic means they are very brittle in nature. So if we can improve the fracture toughness of the ceramic, that means their practical usability improved. So if we see the fracture toughness, this is the third one. Once again with carbon nanotube, we get very good improvement, almost double the value we get with carbon nanotube, which also we get with graphene nanoparticle, but with carbon fiber not much. Then flexural strength, we get maximum improvement with carbon fiber, but a quite good improvement with carbon nanotube. So what I want to say here, that with carbon nanotube we can get all the three properties, hardness, flexural strength and fracture toughness improvement in a reasonable value with say 5 volume %. And as we have the ability to make the carbon nanotube on large scale, so these additives, that means carbon nanotube in boron carbide, we can do it on large scale and make the tiles what is required. Like here we have shown almost 500 hot press tiles are there with the carbon nanotube and boron carbide. Then I'm just discussing how it improves the fracture toughness. So what happens, this is without carbon nanotube. If we see, this is the crack which is through and through. This is through and through crack. But when you add carbon nanotube, the crack get branched or crack deflection or crack bridging. So these are the methods by which you absorb the energy. So you are improving the fracture toughness. That means you are more and more energy is required for the crack to propagate, and that is required for application, for ballistic kind of application. And so again, if we add carbon nanotube to epoxy is very much used polymer. Here also you can see the fracture toughness improvement is tremendous if we add the carbon nanotube. Like here we have shown that this is a collaborative work with IIT Roorkee, that where we could show that with epoxy, if we add the graphene, that's 100% graphene, then 100% carbon nanotube, then a mixture of graphene and nanotube, how the fracture toughness improves. So what I want to bring in to your notice that the addition of carbon nanotube with very small amount of addition, which is below 1 weight%, improves the fracture toughness tremendously, both for polymer matrix as well as ceramic matrix. So with this, how these properties have been utilized in Bhabha Kavach, here I. So before going into that, I'll give a brief overview how a ballistic resistant jacket or bulletproof jacket works. Mainly there are two parts. One is called soft armor panel or SAP, another is called hard armor panel or HAP. So SAP or SAP, it takes our body contour, and hard armor panels, they're not flexible. We combine them like this, that soft armor panel on top of that hard armor. So if I consider this is a full jacket, this is the outer carrier, inside that everywhere there is soft armor panel, and there are some pockets or pouches where we can insert the hard armor panels, like front, similarly from back, or if required from the side. And what was the aim, objective, our objective, because bulletproof jacket was already existing when we started the work. So our objective was to develop a lightweight jacket. Initially the jacket weight used to be in the range of say 14 to 17 kg, and that was heavy, difficult for the movement. So objective was to reduce that weight, then provide multi-hit capability. That means more number of bullets should be hit and then there should not be failure. Then reducing trauma. What is trauma? This is very important. Even a bullet is stopped, then the energy of the bullet, it creates some protrusion backside. So if the protrusion is more than certain value, it can damage your vital organs. So by that way also one person can get killed. Means even the bullet is stopped, even if the bullet is stopped, the person can get killed by a high value of trauma or black face signature. How we measure that? So this is a plasticine, we can call it plasticine material, which is clay type of material which resembles our body muscle, and on top of that we can put the armor panels and hit the bullet from here, and whatever impression is coming on the plasticine, we measure the depth, so that value is called the backface signature of trauma. Now there are different threat levels. So we can only use the soft armor panel, which is the flexible polymers, if we face the threat level from a pistol or a strain gun, which is called level 3A. And if we go for slightly higher caliber bullets like AK-47 mild steel core bullets or SLR, we require hard armor panel, that is the insert, like as I told you. So here, so with 9 mm bullets or strain gun bullets, only this will do. I don't require any hard armor panel. So if I go for AK-47 or SLR, we require this hard armor panel along with the soft armor panel. So this hard armor panel, then only polymer will do. But if we go for further high caliber, which is hard steel core bullets, then we require a ceramic along with, that is ceramic along with the polymer panel. So here I will talk about the highest one, which is level 3 plus it is called. And how the armors are tested means not only we fire the bullet, before that these hard armor panels, they undergo conditioning test, like there will be a thermal cycling for say minus 40 degree to plus 40 degree and minus 60, like that. There is a thermal cycle and with a humidity, and there will be, because when soldier will be using, somebody will be at Siachen, somebody will be at Thar, so the temperature difference is there, and you don't know that this jacket is particularly used for high temperature or low temperature, nothing like that. So one jacket, they should be able to withstand all this temperature variation. Then the SAP, that is soft armor panel, it undergoes tumbling. That means inside a drum there is water, and you rotate the drum with the soft armor panel for 10 days. So that much rotation, and after that you take both of them and then do the drop test. Means this hard armor panel, they drop from a height, and no crack should be generated, because once the crack is generated, that is the flaw. If the bullet is hit there, then it is finished. So after all these tests, you have to undergo the ballistic test. So you know, this kind of harsh condition, the jackets are tested. So I'm just giving the summary of the results. Like this was the normal jackets which our CISF people used to wear, and if you see this much dent, this is called trauma, is there, which is very much visible, which was around 40 to 42. But when we used Bhabha Kavach, where carbon nanotube is used, so there you hardly see the backface signature. And if I see under radiography, X-ray radiography, these bullets, they are all fractured. See, 6 bullets have been shot here, 3 SLR, 3 AK-47, hard steel core, and all of them are fractured and they're captured here. Now, what is the just mechanism I will just want to share, that like a bullet, if it is coming, initially it is encountering the ceramic, which is the you can say the strike face. So once it is coming, the outer jacket of the bullet, it is getting blunt because of the hardness of the ceramics. So hardness of the ceramic must be more than the hardness of the bullet so that it can make the bullet blunt. And the outer jacket, it is ejected, but the inner core of the bullet, it creates cracks. So like this crack it can create and it can penetrate through that. So now these fragmented ceramics, that means ceramics, they have taken the energy of the bullet but got fragmented themselves, as well as the fragmented bullets, they must be able to be stopped by this backing. This backing polymer we have used, carbon nanotube as well as ultra high molecular polyethylene. So initially few layers of these polymers, they get torn up and finally the bullet is captured. So then what happens, carbon nanotube, how it improves? Here a study we have done which is called a DSC, that means differential calorimetry, which shows that the bond strength improves tremendously when carbon nanotube is used, and that is why it requires much more energy to break them. And due to that, you really end up with low level of trauma. That means if you more energy is wasted here, so it cannot penetrate much. So your trauma is reduced. So one thing is trauma is reduced. Second, when you improve its fracture toughness, here also energy is wasted. So you can use a smaller thickness of tiles and smaller number of layers here. By this way, you can reduce the jacket. So whatever jacket we made, the level 3 weighs around 4.7 kg and level 3 plus 6.8, which used to be more than say 12 to 14 kg. So almost 50% reduction of the weight we could do. And I'm just giving, so we can say a jacket with having a size which call a large size, which is 0.6 meters square. It is less than 5 kg weight for level 3. For level 3 plus it is less than 6.8 kg weight. There are some concepts called standalone halves. I'm not going into details. There the weights are further reduced, and these results are based on more than here 70. In fact, we have done, this is results. In fact, we have produced more than 200 samples. We have given to different courses. They have tested in their actual trial conditions and all are satisfactory. So like these are the different variants of Bhabha Kavach. This is a 180-degree protection, that means front and back. This is required for CISF and other elite police forces. The Northern Command, they wanted 360-degree. So we could produce all sides of. Then standalone, I was telling for the CRPF. And this is the ceremony where Bhabha Kavach was handed over by Director BRC to CISF, DG of CISF. And there was a wide media coverage as well. So, and before I stop my talk, once again I would like to acknowledge the contributions of my excellent team members. They are really wonderful, and they finished all the tasks before the time. All these were time-bound job. So, and the mentors and definitely the collaborators from BRC and other institute. With this, thank you all for your kind attention.
Thank you, Dr. Dasgupta, for covering it in a very exactly 1 hour. And I'm sure audience has large number of questions. And I request the audience to post their question in the chat box so that we can take them up one by one. And before the others post questions, let me start. I think there are some questions already, but let me start with the question from my side. You said that it's really heartening to note that the weight has been reduced by 50% and level 3 4.75 kg, level 3 plus 6.8 kg. You didn't refer to the cost. How it compares with comparable products which are available from elsewhere?
Yes, first of all, the level 3 plus we used to import mostly. And if you see the cost of the jacket which now are being made, it is almost half of that of the imported. So that is the main contribution. But now, if you compare, like we have used boron carbide, but if you compare, say some people can use different ceramic as well, which are cheaper, but then you are compromising with the weight. So now if you compare the similar weight, the cost wise it is half of the imported one. And but if you increase weight, then definitely you can use other ceramic to reduce further cost.
Let me read the first question. It is from Mr. Sanat Kumar. Can CNT composites be created with metallic materials, say stainless steels? Say about 6 millimeter thick plates, will it have difficulty? Will it have ductility, impact strength, radiation resistance, and corrosion resistance to water at say 300 degrees centigrade? Can it be machined?
I must say that I have not worked with the metallic matrix, but I know the use. Definitely, the fabricability is not an issue. So there are two methods. If you go by melting route, you can use the melting route, and carbon nanotubes. If you provide the inert atmosphere, it is stable over 2000 degrees centigrade. So there is no difficulty in the structural deformation, but you need to ensure the mixing of them. So that part, if somebody has worked on that, they can tell how they are mixed. But if you go by powder metallurgy route, in some metals they are produced by powder metallurgy, then definitely the powder mixing is not a difficult method. You can easily attain the homogeneous mixture and go by the powder metallurgy route. And definitely it improves. It improves mostly the strength part for the metallic material, because ductility is more in metallic material. So ductility part, it will not improve, but strength definitely improves.
Okay, there's another question from Professor KSS. CNT tend to undergo graphitization. I think I have lost that. Just a second. CNT tend to undergo graphitization during high temperature processing and its effect on impact property. Your comments on it?
Generally, it has been shown that if you are processing by some process which uses impact, so there is a tendency of carbon nanotube breakage and going to the graphite type of form. But whatever it produces, either graphene or carbon nanotube, graphite means it will CNT will unfold, get unzipped, and sometimes it comes into the graphene structure. Both the cases is improve the impact resistance.
Dr. Pradeep writes, thanks Dr. Gupta for a wonderful presentation. I'm wondering if the fluidized bed manufacturing process has been scaled up, and what would be the cost per kg of SWCNT or MWCNT?
Definitely the cost of production depends on the level of production. So at BRC, I can tell we are producing at present 1 kg of carbon nanotube per day, and the approximate cost considering our process is below 10,000 rupees per kg. If you see in the market, good quality multi-wall carbon nanotube, you get 1 lakh rupees per kg. US product. China product you get in the range of 50,000 rupees per kg, but they don't guarantee whether this is carbon nanotube or not, because most of the cases you see the now we have calculated 10,000 rupees in our lab, and we definitely believe that it can come down further if it is produced industrial scale. recently we have transferred the technology of carbon nanotube production by fluidized way to one company, and few more companies have approached, and I feel that maybe within a year you can see carbon nanotube, Indian carbon nanotube getting manufactured at a very low cost, and the unless it cost comes down, it cannot replace the means like carbon black and other things, because you need to have carbon nanotube at a very low price to be utilized as additives. So I think whatever fluidized weight gives, it is very competitive and attractive cost.
Well, I think in addition, there are remarks like it's a very lucid lecture and so on. So I will not go through them. And it looks like everyone is appreciating your talk. So now are there any more questions? I don't see any now. Carbon fiber seems to enhance the flexural strength of B4C, but not the fracture toughness.
Yes.
Why? What is the mechanism governing to contribute flexural strength and fracture toughness respectively?
I would request them, see there is a, if you see that slide one paper we published, if you refer to that paper, we have in detailed analyzed, because here I cannot, because I require a board and all those things to show that how it improves. If you just refer to those papers, you can type my name and then give carbon nanotube, carbon fiber and boron carbide. So you can get those papers. There we have discussed why carbon fiber is behaving in that way and carbon nanotube is behaving in other way.
There is one note from Dr. Pradeep. How do you separate carbon black from MWCNT?
If you see the carbon black, they are basically disordered structure of carbon, which is having very low oxidation temperature. And whenever you get the product, you oxidize them at 350, where carbon nanotube does not go oxidation, but carbon black undergoes oxidation. So this is the method we follow. You can also put nitric acid, concentrated nitric acid for a few hours, but then that process is, I think, time consuming. So the oxidation process is the better process for removing the carbon black from carbon nanotube.
Okay, thank you, Dr. Dasgupta. I hope I don't see any more questions. Over to Mrs. Roy.
I have a question. Do you have the mechanism to control the CNT wall thickness?
At present, no, see, exactly no, but we have control within some value. See, it depends on the catalyst size. So you need to control the catalyst size, then you can control the CNT wall thickness. But there is a definitely variation when we are talking about 1 kg scale. Our variation is, if you see overall 15 to 25 nanometer is the diameter, and the wall number of walls varies between 8 to 13 that we have calculated. That is the variation we can.
Okay. What is the effect of this wall thickness exactly? Could you identify that?
What I have understood, that for practical purpose multi-wall carbon nanotubes, see, if the wall thickness is too much, then you will not get the effect of the nano that way. Means it has to be in that range. Okay. And if your wall thickness is too low, which is having difficulty in production, but it affects the electronic properties mostly, but not the mechanical properties in that.
Thank you. Thank you, Kinshuk. It was a wonderful talk. And most important is that the way you have presented, I think the persons, those who doesn't have chemical engineering background, they also really enjoyed. So thanks again. I thank Dr. Grover also for conducting this meeting very efficiently. And all the thanks to INAE